Hello, this is a second video on operation preserving maps. The first video dealt with example 1 here on page 217. I brought the textbook into this second just to review this definition. If dot 1 is a binary operation on a set S and dot 2 is the operation on set T, then a function that goes from that first set S to the second set T is called operation preserving if, when I take two elements A and B, f of a dot 1b is exactly equal to f of a dot 2 f of b for any two elements A and B in our set. So in this video, we'll be focusing on the second example. Example 2 gives us two different examples to explore. So one is in blue, the second is green. Both of these maps go from the set of the integers to the set of integers. And in this case, it's the integers. F goes from the integers under addition to the integers under addition, such that f of x is the doubling function. You give me 2, I give you 4. You give me 3, I give you 6. Anything you give me, any integer value that comes into this map comes out twice that. So we want to explore what is the goal. Well, again, we set up the goal based on the definition. F of x dot 1 y is going to be f of x plus y. Because again, both of these maps are under addition. We want that to equal f of x plus f of y. And if we can show that, we're done. So we do a little scratch work first to figure out exactly what is f of x plus y. Well, again, this is the doubling function. So whatever element I put into this function, when it comes out, it's double that. So I double this element, 2 times x plus y. And then I use a distributive property for integers, because I know that holds true. And I distribute this 2 to both the x and the y to get 2x plus 2y. It's about as far as I can go algebraically with this statement. So I shift to the second part, the conclusion of my goal. That will be f of x plus f of y. And I want to show, where does f of x map to? Again, this is the doubling function. So x under the map becomes 2x. And y under the map becomes 2y. I like this. I can see that these match. So now it's up to me to set up the short proof that starts from the goal statement, one side, moves through the algebra to reach this conclusion, f of x plus f of y. So I start over here with my formal proof. F of x plus y equals, where does the map take the element? To 2x plus y. I just applied the map. Now I distribute that 2 because the integers enjoy a distributive property, 2x plus 2y. Give a little justification, and then make a conclusion. Hey, this is where I would have mapped the element x, exactly to f of x. And this is what I would have mapped y to, f of y. There's the conclusion of the proof. F of x plus y is exactly to equal to f of x plus f of y. Again, I apply the map, do a little algebra, justify that algebraic step, and then hope that that is where the map would have taken those elements in the first place. To see that this is quite a special case, that there are other maps that don't satisfy this operation preserving condition, let's explore this second part of example 2. Consider the same map, f, going from the integers to the integers, but this time the integers under multiplication. So now f is going from z under multiplication to the integers under multiplication, such that f of x is exactly 2x. As a reminder, that would take an element f of y to double that, 2y. First, we examine the left-hand side of our goal statement. All right, we've got to come up with that goal statement, right? We want to think, what are the operations in the first set? What is the operation in the second set? And grab two elements. So I get f of x times y, multiplication being the operation in the first set, equal f of x times f of y. Again, this is my goal. So I look at the left-hand side of the goal, f of x times y, and I apply the map to that element, x times y. That'll be 2xy. And that's about as far as I can go algebraically. So I look at the right-hand side, f of x times f of y equals double x and double y. So 2x times 2y. Well, I look at that a little bit and think I've got a commutative property in the integers, so I can gather those 2's. I can bring those together and multiply them to get a 4, and I found 4xy. Do you see these two highlighted values? They are not a match, which indicates that I can stop right there. I don't need to draft a proof for this because this map is not operation preserving. Hope this is helpful to see some of the scratch work and the groundwork and some of the thought processes behind the proof for an operation preserving map. Good luck to you on your work.